Okay, good morning. So the day we were also excited about, Monday. So we are going today to go over some new material. We're going to finalize chapter 2. And then we're going to go into chapter 3 and talk about a couple of important things over there. I know many of you were anxious to know what is on a test. And as I said, tests are cumulative generally. So they're covering everything from the beginning till whatever we studied today included. Now, today we're not going to study too much. We are only going to talk about something. Pretty much we're going to talk about general algorithms, and we're going to talk about big O notation. And generally, it's not the horrifyingly complicated topic. So hopefully all of you are going to have an easy time with that. On Wednesday, we're going to be having a review session. So bring in questions. I'm going to be just answering questions during the Wednesday. And then Wednesday during discussion, you're going to have an assignment to work on. It is going to be collected. It is going to be review questions from everything we have studied so far. So it's going to have like maybe a set of shorter questions you have to know how to do. Our test is going to be on Wednesday at 6:30 p.m. It's going to be a 1-hour test. So it's going to be from 6:30 to 7:30. Please do not be late. We are going to talk a bit more about test again on Wednesday. So you need to know everything we covered in chapter 1. You need to know everything we covered in chapter 2. And you will have to know how to do the big O notation, but it's only going to be one simple question on the test that I can promise you. Now, one more thing. Due to the fact that hopefully all of you are now working on your homework assignment from section 2, 2.3 and 2.4, due to the fact that you have a test on Wednesday, so hopefully you're already practicing by doing the homework. What we are going to do is this Friday, we are not going to toss the coin. Instead, I'm just going to be collecting homework. So I think one test per week is enough. So you do not need also to prepare for the quiz on Friday. Friday is going to be a collection of a homework. And as I said, I highly recommend doing homework before the test because, again, it's a practice. And this topic is on the test too. Questions? So if there are no questions, let's move on. So here we go. I'm going to show you a video. Hopefully you're going to enjoy it. Please type after the video starts if you can hear it or not.
In the 1920s, the German mathematician David Hilbert devised a famous thought experiment to show us just how hard it is to wrap our minds around the concept of infinity. Imagine a hotel with an infinite number of rooms and a very hard-working night manager. One night, the infinite hotel is completely full, totally booked up with an infinite number of guests. A man walks into the hotel and asks for a room. Rather than turn him down, the night manager decides to make room for him. How? Easy. He asks the guest in room number 1 to move to room 2, the guest in room 2 to move to room 3, and so on. Every guest moves from room number n to room number n plus 1. Since there are an infinite number of rooms, there is a new room for each existing guest. This leaves room 1 open for the new customer. The process can be repeated for any finite number of new guests. If, say, a tour bus unloads 40 new people looking for rooms, then every existing guest just moves from room number n to room number n plus 40, thus opening up the first 40 rooms. But now an infinitely large bus with a countably infinite number of passengers pulls up to rent rooms. Countably infinite is the key. Now, the infinite bus of infinite passengers perplexes the night manager at first, but he realizes there's a way to place each new person. He asks the guest in room 1 to move to room 2. He then asks the guest in room 2 to move to room 4, the guest in room 3 to move to room 6, and so on. Each current guest moves from room number n to room number 2n, filling up only the infinite even-numbered rooms. By doing this, he has now emptied all of the infinitely many odd-numbered rooms, which are then taken by the people filing off the infinite bus. Everyone's happy, and the hotel's business is booming more than ever. Well, actually, it is booming exactly the same amount as ever, banking an infinite number of dollars a night. Word spreads about this incredible hotel. People pour in from far and wide. One night, the unthinkable happens. The night manager looks outside and sees an infinite line of infinitely large buses, each with a countably infinite number of passengers. What can he do? If he cannot find rooms for them, the hotel will lose out on an infinite amount of money, and he will surely lose his job. Luckily, he remembers that around the year 300 BCE, Euclid proved that there is an infinite quantity of prime numbers. So to accomplish this seemingly impossible task of finding infinite beds for infinite buses of infinite weary travelers, the night manager assigns every current guest to the first prime number, 2, raised to the power of their current room number. So the current occupant of room number 7 goes to room number 2 to the 7th power, which is room 128. The night manager then takes the people on the first of the infinite buses and assigns them to the room number of the next prime, 3, raised to the power of their seat number on the bus. So the person in seat number 7 on the first bus goes to room number 3 to the 7th power, or room number 2187. This continues for all of the first bus. The passengers on the second bus are assigned powers of the next prime, 5. The following bus, powers of 7. Each bus follows powers of 11, powers of 13, powers of 17, etc. Since each of these numbers only has 1 and the natural number powers of their prime number base as factors, there are no overlapping room numbers. All the bus's passengers fan out into rooms using unique room assignment schemes based on unique prime numbers. In this way, the night manager can accommodate every passenger on every bus, although there will be many rooms that go unfilled, like room 6, since 6 is not a power of any prime number. Luckily, his bosses weren't very good in math, so his job is safe. The night manager's strategies are only possible because while the infinite hotel is certainly a logistical nightmare, it only deals with the lowest level of infinity, namely the countable infinity of the natural numbers, 1, 2, 3, 4, and so on. Georg Cantor called this level of infinity Aleph 0. We use natural numbers for the room numbers as well as the seat numbers on the buses. If we were dealing with higher orders of infinity, such as that of the real numbers, these structured strategies would no longer be possible, as we have no way to systematically include every number. The real number infinite hotel has negative number rooms in the basement, fractional rooms, so the guy in room 1/2 always suspects he has less room than the guy in room 1, square root rooms like room radical 2, and room pi, where the guests expect free dessert. What self-respecting night manager would ever want to work there, even for an infinite salary? But over at Hilbert's Infinite Hotel, where there's never any vacancy and always room for more, the scenarios faced by the ever-diligent and maybe too hospitable night manager serve to remind us of just how hard it is for our relatively finite minds to grasp a concept as large as infinity. Maybe you can help tackle these problems after a good night's sleep, but honestly, we might need you to change rooms at 2 a.m.
Oops. So let's say you have to read an incredibly long email from your
Can you hear me? All good, great. So how did you like the movie? It's fun. How is it connected to what we have been doing on Friday? Well, if you remember, on Friday, I said we're going to talk a little bit about countable versus uncountable sets. And I reminded you what cardinality is the number of elements in set. Now, when I have a set of all students in this class, for example, it's definitely countable and finite, correct? So we know exactly how many people we have in this class. Now, but surprisingly, countable is not just finite. So countable and finite are not synonyms. They're not meaning the same thing. Countable, it means you can count, but there are infinitely many countable numbers, correct? So you have 1, 2, 3, 4, 5, and you go to infinity. They're all still countable. And this is exactly where he talked about Aleph 0, which is a cardinality of natural numbers. It talked about how you can take infinite many numbers, and actually you can double infinite many numbers. If the first ones were countable, when you double it, you still get countable amount. So there is countable infinity, and then there is uncountable infinity. And the uncountable infinity is going to be set of reals, for example. We cannot count them. So how do we decide if something is countable or not? So what we do is, first of all, we need to decide how can we compare infinite cardinalities, because they're infinite, correct? How we can compare different infinities? They seem like they should be the same. Infinity is infinity. And actually, they're really not. So we are going to say that A and B are going to have the same cardinality if there is a one-to-one correspondence, which is a bijection, so meaning one-to-one and onto function from A to B. In this case, we're going to say that two sets, A and B, have the same cardinality. Now, if you remember what they did in the cartoon, which is quite amazing, first they say, I can always say F. So you can talk about how all even numbers, for example, or all how you can take every x and make it 2x. So what type of function I have if x is inside integers or countable numbers? So countable numbers are going to be natural numbers. So it's 1, 2, 3. So n does not have a 0. Now, in this case, if you hear, I have n here, but what I have here is actually even n, correct? And this function is one-to-one and onto, correct? You should be able to prove me that f of x equal to 2x is going to be one-to-one and onto. I'm not sure about ontology, Zach, so I'll have to check it. Now, it is onto because you're going to be able to get any even number, correct? And you can pass every x and you're never going to land up at exact same thing. You can do similar trick with odd numbers. you can do many different things. So there's, for example, infinitely many prime numbers, and you can generate a function f of x such that x goes to x's prime number. And we know we have infinitely many, so you should still do it. Yeah, so David, onto and surjective are the same thing. You're right. So the other way to say it's surjective. Yes. So what does that mean to us is that cardinality of n is actually equal to cardinality of even n, which is to some extent strange, right? Because we kind of know that n is supposed to have more numbers than even n, but it's still the same due to the infinity. And this is not exponent. This is x's. You can type it like this. This is like first prime number, second prime number, third number, fifth prime number. So x's prime numbers. This is what it is. It's not an exponent. This is like English ending of the word. So this way you can show that number of prime numbers is as infinite as number of natural numbers. I think cartoon kind of showed it in the best way because you kind of could see it and hopefully grasp a little bit better on the idea. But if you think about it, what he did, he was always giving you a function, correct? Of how to map things, what to do with the mapping. And this is interesting. So what do you need to remember? Well, you need to remember that is not countable. Now, integers are countable. And let's think how you can do it. Well, one of the ways to think about it is you can send all the positive numbers like 1, 2, 3, 4, 5 into evens and all of the negative numbers into odd numbers. And here we go. You covered the minus z and plus z, correct? And it all mapped into a countable amount of numbers. So there are different functions you can get. So definition. A set that is finite or has the same cardinality as the set of positive integers called countable set. Countable set has cardinality of alpha 0. Alpha is the first letter of Hebrew alphabet. So this is where it came from. What we know is positive odd integers are countable, even integers are countable, odd integers are countable, integers are countable. So there are tons of countable sets. You can come up with prime numbers are countable, but then there are also tons of things which are uncountable. And an example is going to be real numbers. You can also think about how imaginary numbers come to place. So how do we draw a symbol? Yeah, so you have a line and then you have two curly things like that. So it's not really X because those two lines, they're separate. Well, the other way to write it is like that, but this is not capital. So this is the capital alpha. Okay. Great. Yes, and then the second one is beta, which is going to be the real number thing, but yeah, we do not need to know it. But alpha 0 is a good one to remember. Okay, so guess what? This concludes chapter 2 for us. So what we have covered in chapter 2 is we started with the traditional sets and we defined what a set is. So keywords for the set. What are the keywords for the set? Unordered, unique, distinct, unordered. Good. We remember that. Then we talked about different set operations, how you can union sets together, intersect sets, and so on. We also talked how we can check if two sets are equal to each other and prove if they're equal to each other or not by saying, if I take a member of this set, I need to show it's a member of the other set too, and vice versa to make it similar. We talk about subsets and so on. So then what we did is we talked about functions, correct? And we defined that function goes from one set to another. It maps elements from one set to another set. Now, one thing to remember when we talk about functions is in order to be a function, can I have something like that? No. Okay. And another question. Can I have something like that? Can I have somebody who is not mapped? No. Okay. And this is something important to remember. So what do you think? F of x equal to 1 over x. And I am going to go from integers to reals. Is it a function? One over x. Is it a function? And why no? 0 isn't mapped, correct. So you need to subtract 0 now. It is a function. Now, I know for some of you who took calculus and pre-calculus, right now what I said is kind of equivalent to, oh my God, it is function, it is traditional function, we study it for so long. But really, if you think about it, in order to be a function, you need to map everything. So you kind of, this is why generally in like calculus and other stuff, you're always going to write something like that, right? So this is kind of saying, I'm not allowing x to be 0 because it's not defined in this case. And now it's a function. So remember, it's important. Those are little things, but they're really, really important things. This is a big difference between traditional calculus or pre-calculus class and discrete structure. Because in here, you cannot say if x is not 0, then it's function. I gave you the set. I said I want it to be from Z. Okay, let's see. Question. So yes, you are going to have some proofs. Remember, you only have 1 hour. So I'm not going to let you prove something horrifically complicated just because you do not have enough time. Okay, but yes, you can anticipate at least one proof or maybe a couple. So I do not consider proving a function as one-to-one or onto really proves. This is a question on a function, but you can anticipate to have a question on a function if it's one-to-one or onto. You can put whatever you want on this one piece of A4. You can use as small of a handwriting you want, as long as you can read what you wrote to yourself. So yes, I would suggest going over your notes, picking up the most important things. I generally do not allow to take anything to my tests, but I decided to reconsider because I think it's going to be a good exercise to see if it's going to help you guys out or not to have this one page. I think it's an interesting to see what exactly you're going to put out there, because you need to put the most important things. You can put definitions you think you're going to forget, right? You can put some rules on how to write proofwriting. Yes, it's a traditional A4 piece of paper, like something like that, A4 piece of paper on one side. You can put as much as you want on it. Like normal printer paper, correct? Nice. So back to what we studied in chapter 2, we did functions. After we talked about functions and properties of one-to-one and onto, which were important because now we can compare if two sets have the same amount of elements, correct? Because actually what it means to have an inverse function, that means you can pass elements back and forward. Now, somebody asked me during an office hours why the inverse function is important. And since I didn't mention it, and I probably should, do you like using your credit card? Like, do you like your credit cards if you have one, kind of? Probably, yeah, it's useful, right? So when you use your credit card, do you want your information to be stolen? Probably not. You want your money safe, correct? So that means you want the information to travel securely, correct? While it checks if you have money on credit card or not as you pay it. So that means you probably want to use some type of a security protocol. But what does it mean to use a security protocol? What it really means is you're taking the information and you're sending it to a pretty much kind of bank, you can think about it, and verifying it. When you send it, you want it to be encrypted. You want to use some type of a cipher, right? Now, if I use a cipher, should I be able to unscramble the information? Think about it. So I sent my information securely, I scrambled it so that nobody can understand it if he gets it. And then the correct person got it and he's supposed to be able to get it back. Is it important for him to get it back? Yes. Well, actually, think about it. This is actually a function because what we are doing is we are taking information, we map it, correct? We do something to it. And what we want is we want the inverse function to exist. Does it make sense? So inverse functions have tons of real life applications. It's an important property and we want it. Finally, what we did after we talked about functions is we also talked about sequences. Sequences are kind of like a functions. They have some idea where you can plug in instead of n generally countable numbers, and you can create sequence which is not continuous, so it's only going to be generally integers, and this is like a function. It's going to generate a set of numbers for you. It's going to generate actually a sequence because things can repeat, and it also has a lot of important properties. We program using recursive ideas sometimes, and sequences and recursion come together really nicely. And finally, we finalized by talking about the cardinality of a set and how to figure out if two infinite sets are having the same amount of elements, have the same cardinality. Okay, especially since it's infinity, it's kind of strange to understand. So this is what we did in chapter 2. Now, there is no homework assignment from section 2.5. This is more of a for your understanding chapter. So next we're going to go and we're going to start talking about chapter 3. Now, first of all, let's see. Chapter 3 is actually talking about algorithms and some other things. So first of all, let me define to you what algorithm is. An algorithm is a finite set it's a finite sequence, not set. You can repeat stuff, so it's a finite sequence of precise instructions for performing a computation or for solving a problem. Here is an example. I have a problem. I have a family who is starving and they want dinner. So guess what? I can create an algorithm for cooking a dinner for my family, which is going to specifically state the tasks I'm going to be doing what at a time. So I don't know what are we going to do today. For example, we're going to fry chicken or whatever. So I will have an instructions like one piece at a time. So I probably should turn on oven, correct? Maybe put some, get some chicken. Yes, maybe even go and buy some chicken first. Agreed? And so there are sets of instructions of what I need to do, and I'm going to put them into correct order. And there are restrictions. I cannot, for example, fry chicken before I buy it, correct? So those steps are actually going to come in some specific order. Okay. Now, please do not put things in chat unless it's class related, because it does take my attention because I'm trying to read it in case those are questions which are related to me. Okay. Now let's go back to the algorithms. So here is an example of an algorithm. I want to find maximum value in a finite sequence. So what I have here is I have a sequence. And what I want is I want to find the maximum value. How can we do it? Well, in order to do it, I need an algorithm. So I need to specify the directions. In order to find the maximum here, what I can do is I can say, okay, I'm going to be remembering what maximum element I have seen so far. So I can start with element 1 and I can say, okay, the maximum I have seen so far is going to be A1, correct? Then what I'm going to do is I'm going to say, okay, now let's look at the second element and let's compare it to my maximum element. Who is bigger, max element or A2? Well, who knows? But if a maximum is smaller than A2, what should I do? If the value in A2 is larger than the maximum, then A2 is going to become a maximum. Okay, correct. So I can write it in words. I can say put A1 as current max, move to the right one element at a time, check if that element is larger than current max. If larger, replace current max with that element. Do it until you run out of elements, correct? A lot of words. So what we generally do in computer science is we like to write pseudocodes. Pseudocodes generally are more structured ways which use less words, but they also use some mathematics generally or some expressions. So here is what I can do. So I have a procedure which is going to be called max. It's going to accept the sequence S. And then here is what I'm going to do. I'm going to say max is going to get A1. My S is A1, A2, AN. And then I can say something for I equal to 2. So starting with element 2 to n until I reach element n, what I'm going to do is I'm going to say if max value is less than the value at place I, then I need to replace my max, correct? I'm going to say max is now getting value AI. And then at the end, I can say something like return max, because what is going to happen? Max has the largest element. So what I just wrote for you is called pseudocode. Anybody who took any type of a computer science related class before, you probably saw something similar. It is kind of close to a programming language, but it uses a lot of words as you do it. So if you think of algorithms, they generally defined using input you get and output you want. So in this example I just gave you, my input was sequence, correct? And my output was max value. So what I really want, it's kind of to define of what I want in the algorithm. I need to specify what I'm going to give you and what I'm going to get as an output. Back to my not so successful dinner example, my input can be a chicken and the output I want to get is fried chicken, okay? And there will be directions on how to cook it, for example. This is going to be a real life algorithm. Another algorithm is how to wake up in the morning, for example, right? There are good algorithms and there are bad algorithms on how to wake up in the morning. Who can give me an example of bad wake up algorithm? Turning fire alarm is a bad algorithm for wake up? Yeah, I agree. Fire alarm was not something I thought of. And yeah, wake up and don't get out of bed for 30 minutes is another good one. Yeah, if I wake up, okay. So yeah, we have different type of things, but generally my algorithm can be to set up my alarm clock, correct? And then hopefully my good algorithm for waking up and getting to school is going to be to turn off the alarm, get out of bed, go brush my teeth, correct, dress up, get breakfast and go to school. Yes, this is a good algorithm and probably effective algorithm. Now let's talk about a different algorithm. So to put on the clock, and when it goes on, I'm going to snooze it and snooze it and snooze it like for 50 times and probably going to be late to school, correct? So this is not going to be a good efficient algorithm, right? So when we talk about algorithms, there are efficient algorithms and less efficient algorithms. So what type of an example of inefficient algorithm for the previous time I could give you? An example is going to be randomly pick a value and check if it's bigger than my maximum, and then randomly pick it again and randomly pick it again and randomly pick it again. It's going to be a bad algorithm because it's probably not going to give me a good result, and I even don't know how many times I'll need to run it before I actually get randomly every possible element in the sequence, correct? So this is not going to be a good idea of how to do things. What it means is we kind of need to have an idea of how to analyze algorithms. There is this whole algorithm analysis class in computer science, which talks about efficient and not efficient algorithms. One of the things we need to learn from mathematics is we need to talk about growth function. So we are in section 3.2. This is the one you need to know for the test. So it's called the growth function. So let f and g be functions from set of integers or real numbers to set of real numbers. We say f of x is big O of g of x, and we literally say it big O of g of x if exist c and k constants such that f of x, and this is absolute value here, is less than c of g of x for all x bigger than k. Example. So let my f of x be x cubed minus x squared plus 1. And I'm going to show you f of x is big O of x cubed. So O of x cubed. This is how I'm going to write it. Now, first of all, it is a bit surprising because guess what? Who looks bigger to you? X cubed minus x squared plus 1 or x cubed? They're kind of similar, kind of different. How can I show it? So what we really want is we kind of want to show that if you have a function, I want to find a function which is going to bound it from top, okay? Now, sometimes it can be bounded by the bottom like this, but if I'll multiply this line, dotted line, by c, I can get up, correct? I can move this line up, and then it's going to be getting it from the top. So how do I show you that f of x cubed minus x squared plus 1 is actually big O of x cubed? I need to show you that I can bound it for some constant. So there is a constant c for which this works. And I need to find you this constant. And here's how I can do it. So x cubed minus x squared plus 1 is going to be less than x cubed plus 1. Do you agree? Why? Well, x squared is always positive. Do you agree? Yes. When I subtract something positive from a thing, do I make it smaller or larger? I have a value and I subtract something from it. Yes, I'm probably going to get it larger. So what I can say is I can subtract the minus x squared. I can get out of it and then make the whole expression larger, correct? So my right side now is bigger than the left side because I'm not subtracting something positive from it anymore, right? Now, who is bigger, x cubed or 1? Yep. And in this case, I'm going to do x bigger or equals 0. Yes, just to make sure. So, do you agree with that statement out here? Do you agree that x cubed minus x squared plus 1 is less than 2x cubed? Yes, here we go. So I found my constant. 4c equal 2 and x bigger equals 0. That will always work, correct? So after that, my function is always going to bound it. Now, what is the whole big idea here? Oh, how can I assume that all numbers only include positives here? Remember in my definition, which you probably didn't see it yet, it can be I only interested when x is bigger than something. And in my case, I picked up x to be bigger than 0. It doesn't have to be for everything. It has to be, it's kind of like looking at the infinite limit of positive infinity. So you want to bound it for large values. Why is that important? So generally, when you think about algorithm, you work with some type of set or some type of a sequence, and it's a huge sequence. So you want to know how your algorithm is going to work for huge sequences. You are not interested to see how it's going to work in like for small sequences. And we generally try to bound it to common things like x squared or x cubed. So here is a theorem, and pretty much this is kind of the only thing you need to know for the test. You need to use it. So assume you have a polynomial function. That means it has a form of constant multiply x to the power and many terms like this. Then fx is always a big O of x to the power n. And again, all of my an is bigger than 0. So what does it mean? What it really means is you do not need to think twice. So if I have fx equal to x squared plus 1 multiply x minus 5, this function is big O of what? So in order to do it, I need to find the hugest, the largest, let me make it 2, the largest term out here. So most common mistake is to say it's going to be x squared. It's really not. When you talk about polynomials, I need to open up the parentheses. So when I open up the parentheses, I have 2x cubed plus 2x minus 5x squared minus 5. Now I'm ready. Now what is my largest power out here? X cubed. So this function is big O of x cubed. Now, what happens to my constant? Well, 2x cubed is always less than 3x cubed, correct? So by definition, it's always f of x cubed. We drop constants. So rule 1, drop constants. Rule 2, find largest term. On that note, we are done for today. Have a good day.